exponential function is the inverse of the ln x function. Okay, so please keep this in your mind, even though maybe you don't have time to study the reason, but please just keep your, at least you should keep this in your mind, that the exponential function actually is the ln function's inverse function. Okay, and then the second thing is when the original function composite the inverse function, that means exponential function composites ln function, then we can get the identical function. Okay, and likewise, that if we just use ln x function to composite exponential function, we also can get the identical function back. Okay, so this is the second thing I want you to remember, right? And I also want to remind you that there are 4 rules for the exponential function. So here, I just have a quick review for you. Then I believe you, if you have already studied it, you know that, right? And then about the derivative of the exponential function, actually based on the theory of in the chapter 1, in the section 1, we know that based on the rule, we can get that the derivative of exponential function is still exponential function. So also please keep this in your mind. And we can just extend the derivative function from the original exponential function to e to the power of u, where u here is a differentiable function of x. Then we can get the result. So actually, if we just differentiate e to the power of u, the result will be still e to the power of u, but you still need to have du over dx because of the chain rule, right? Then I also use this part to prove that e number can be expressed as a limit where e is equal to limit x is approaching 0, 1 plus x to the power of 1 over x. Okay, so you also can convert it just like this, right? Then finally, before went to the end of last class, we just extend the exponential function to a general exponential function. So the so-called general exponential function, that means the base is not just e, but a. But a here should be positive number, like 2, 5, 10, 11, blah, blah, blah. Any real number is fine. But the only condition is a should be larger than 0. It's a positive number. Then we can just extend the idea from exponential function to a general exponential function like this. A to the power of x can be expressed as e to the power of x times ln a. So again, if a here is e, then you can just find it will be reduced to the normal, the original exponential function, e to the power of x. And then we also try to understand the behavior of y is equal to a to the power of x. So through first order derivative and the second order derivative, we can get the result. If the base is larger than 1, then the function will be an increasing function. But if the base a is less than 1, then you can see the curve will become a decreasing function. But no matter a is larger than 1 or less than 1, this curve will always be concave up because the second order derivative is positive. Okay, we also learned this part. And then next time I will just show you a very special case for the power function. like this one, x to the power of x. So the result is just like this. And then we also learn how to integrate a to the power of u. Then the result is like this. Here, you need to memorize the result. If you just integral a to the power of u, the result will be 1 over ln a times a to the power of u. Okay, so that's all about what we just learned last time, just this Monday, right? So it seems that there are so many formulas you need to memorize, but no worries. If you try to derive the result by yourself, that will much impress you. 也许这边有很多公式哈，特别下学期半学期有很多公式，那不用担心。如果你可以的话，推论过一次哈，你的印象会比较深刻，了解吗？好，就是自己去推过一次之后呢，有些印象就会比较深刻。那如果真的不行，没关系，要么就先记下来使用哈，因为我们大部分都还是用的角度来看它了哈。Okay, so let's just start. So, is any problem? Any questions? No? Okay, let's just continue. Okay? So right now, let me just quickly have the new we just check the whole learning process. We learn from ln x, right? And we also learn e to the power of x, right? They are inverse functions for each other, right? And then right now we already learn a to the power of x, right? It's a general exponential function. But today we will go into logarithm a based x function, right? So right now we already learned these three functions, but today we will focus on this function. Okay, so we just start by the definition for logarithm a based x function. If a is positive and a is not equal to 1, a based logarithm function of x is the inverse of a to the power of x. So you can see they are inverse function for each other. So here we also have a similar relationship between a to the power of x and logarithm a base x function, right? So here, it's quite I should say it's quite intuitive, right? So we can expect the result will be when we use the function to compensate its inverse function, then we can get identical function back. So s here should be positive. Okay, so similarly, if we have logarithm a based a to the power of x, the answer is still x, but here we will focus on all x will be all x, because you know when we compensate f compensate g function, the first function we will encounter is a to the power of x. So we will follow the range, the domain for a to the power of x. Okay, so x should be all x, all x. So if we want to evaluate logarithm a base x, then so right now we want to evaluate, then since a to the power of logarithm a base x is x, right? Here, the result just directly come from here, right? Then we try to take the logarithm at the both sides. A log a x, then x, right? So here we already have the equality. So at the both sides, we take the value of logarithm at n function. So we still keep the equality, right? Then we can follow the n function rule. So here we can move the power up down to the coefficient, right? So here, this part can be moved here, so we can continue to get times ln a is equal to ln x. So finally, we can get ln a base x is equal to ln x over ln a. So this is a happy result. Why I say that? Because you can see it's a normal logarithm function. We can just convert it into n function. This is the general one. This is the very specific one. So I believe you also learned this idea when you was a high school student, because it's just like we just change the basis, right? 换底有没有学过 ？log 函数可以换底 ，right? Just you learn before. I believe you also learn that you can say that okay, like log 10 base 15. You can just maybe I will not use 10. Like okay, 2. It can be changed as log 10 base 15 over log 10 base 2, right? So you can see the base will be from 2 become 10, right? But so you can see there is very similar result. This is a base logarithm function, but we can change it as ln function. So sometimes we will regard ln function as is e based. So you can just kind of regard that ln x is equal to log e base x, right? So you can also regard this part as log e base a, right? So the behavior is quite similar to this one. Okay. But the second thing I want to emphasize that please just keep this in mind. In the future, if we just encounter the general logarithm function, please try your best to convert it into ln function. 未来如果你看到这种 log 的函数的时候呢，记得就尽量把它往 ln function 去做转换。因为当我们把它换成 ln function 的时候，如果是微分、积分，我们都知道它的结果，比较知道它的结果。Okay, so there are also 4 rules for the general logarithm function. The first one is log a base sy is equal to log a base x plus log a base y, right? And the second rule is from the division to subtraction, right? And then we can also find that the result is minus log a base y the last part is log a base x to the power y. It could be, we can just move the power, become the coefficient. So we can get y times log a base x, right? So this for rule, I believe you just learned logarithm functions before. When you was a high school student, you learned this before, right? You learned this before. This for what? Right? So I also give you a very quick very quick approval about this part. That so in the earlier section, we already know ln x y is equal to ln x plus ln y. Do you still remember this? Originally, this is multiplication. Then through ln, we can make multiplication become addition. Right? Here is multiplication, and here is addition. Right? So we have this result. And then we just divided both sides, divided by ln a and ln a and ln a. Right? So you can see here will become a logarithm a base sy is equal to logarithm a base x plus logarithm a base y. So easy, right? It's true. It's true. So we can get actually equals because of this, right? Two things. The first one is based on the normal logarithm function. Then based on this, we just divide ln at both sides. So we can have this, and then have this, convert this. Originally, we know this is this one, right? Then right now we just follow the opposite direction, then we can get logarithm a base sy is equal to this one. Okay, so let's just result, and then we will continue to find the derivative involving logarithm a base u. Here, where u is a differentiable function of x. So that means u is blah 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 x plus blah 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 x, right? So when you just encounter this, I want to differentiate this. So what you should do, the first thing you need to do is original I want to differentiate this one, right? This is a purpose. This is our purpose, right? Then you should try to do this. Just convert it, become ln u over ln a. Just like this, right? Here. When you encounter this, try to convert it into a normal ln function. So here, I just change it from here to here, right? Then you will become, because this is constant, so we can just move it out ln a, 1 over ln a, right? Then we try to differentiate this one. So what's the result? What is the result? 1 over u times du over dx. Yes, correct. So please just remember the result here will become here. So if you want to regard this as a formula, maybe it's not that easy for you to memorize. But once you just convert it into an function, it's easy for you to derive the result by yourself. 如果要你去记这个公式的时候太多了，所以我是很建议说你一定要记它，你自己推一次看看，就过来会得到这个结果。推久了，记久了自然就记下来。那一开始有时候是 LNA 在上面，是 LNA 在下面，就积分，有时候微分，就有不一样的结果。那你自己推过一次以后，你就比较印象深刻，说这个应该是摆在分子或分母。硬要去记这个公式，有时候好像意义也不是很大。Okay, so we can have a quick example that, for example, if we want to differentiate logarithm 10 base 3x plus 1. So by following this, so the first term will be 1 ln 10. Then we will have 1 over 3x plus 1. Then we need to differentiate u, right? U here is u. Here is u, right? Just like here. So the next thing is we need to differentiate 3x plus 1. So the answer should be 3. Then finally, the result will 3 ln 10 times 3x plus 1. Okay, so this is about the derivative involving the general logarithm function. Then, so if we face this, so this is about how to integrate some function which is related to the general logarithm function. So similarly, we just convert this part into logarithmic function, general logarithmic function. Then it will be here, right? So you can just find that I always convert the general logarithmic function to LN function. So it's the key. This is the key. 但技巧就是你看到 log， 就记得把它转成 ln， 然后再来做进一步的计算。Okay, so that you can see 1 over ln2 is a constant, so we can just move it out of the integral, right? Only lnx over x will be left, right? So it will become 1 over ln2 integral lnx over x dx. So you can see here we can regard it as u. So what I'm trying to do, I'm trying to use substitution to make the integral simpler. Can you find that? Because original lnx over x is hard for you to integrate, right? So right now I try to let u is equal to lnx. That means I will try to use u to replace lnx. But we always know that once I assign assign lnx to u, then the next thing we need to do is du dx, right? Because we need to replace dx with du, so we need to do that immediately. So that will be 1 over x, so that dx will be du dx will be du could be du over x, right? So you can see I can replace this part by this one. I can use this part to replace this one, right? So finally, we will see it will be 1 over ln 2 integral u times du, right? Because this part will be replaced by du, and this part will be replaced by u. So finally, I will encounter this integral. So this integral is very easy. So this is a result. It will be 1 over ln 2 1/2 u squared. Yes, correct. Plus c, right? Then remember, let's just that u is ln back, right? So finally the answer will be ln 2 times ln x squared plus c. And please just remember, this is not equal to ln x squared. Remember, the bracket is very important. This is very important. This is not different from before, right? Because this is ln x times ln x, but this is ln x squared. So you even can move the power to become its coefficient. Right? So it's different. It's different. So this part is section 3. So this is section 3. And about the section 4, I will skip section 4 because section 4 will just explain some exponential change, and then section 4 will just illustrate some separable differential equations. So for the second, for this part, we will not include it. We will not include it into the scope of our quiz or even examination. But I hope if you can spend some time to study this part, is even better for section 4. But I will skip this part because this part will be discussed in your further class, especially for differential equations. 在那个其实是我们讲的是有一点是跟微分方程式有关系的，有一个部分是跟那个exponential function 的那些行为，所以那部分我们就不考哦。但是不考不代表它不重要了哈，是希望说那部分因为后面的课程里面会涵盖到，所以我们就不特别花时间去讲了哈，因为我们讲的也是皮毛而已啦。在微分方程式的时候应该都会讲，所以我们这部分就跳过去哈，我们就只会跳到7至5。OK， so let me just Let me see. And next section should be 7. Sorry, let me check. Okay, I find it. Okay, so we just direct go to. So we just skip section 4. We just directly go into section 5. Section 5 is indeterminate form and error has Hapital-Zero. So later I will explain what is indeterminate form is. Then based on this form, we can use the Hapital-Zero to differentiate it. So the first thing I want to introduce to you is about the indeterminate form. So as the indeterminate form, what is the indeterminate form? So as the indeterminate form will include 0 over 0, infinite minus infinite, or infinite times 0. So this is the indeterminate form. So why we call it indeterminate form? Because if we will encounter 0 over 0, actually we cannot have this form. But if you just encounter 0 over 0, the result is hard to say. We cannot conclude it immediately. We need to have some calculation that find the right result. So for example, if 0 over 0 or infinity minus infinity, sometimes the result could be 0. It's possible. It could be any number, and it could be infinity, positive infinity or negative infinity. All of them are possible. So if you just encounter infinity times 0, 0 over 0, infinity minus infinity, it's hard to say. So all of them are possible. Okay? So if you just encounter this part, you can just use the Hapital-Zero to get the limit. So let me just, so when you just encounter, so I will show you that the theory about the Hapital-Zero. So what is this? In the past, when we try to calculate the limit value f of x over g of x when x is approaching a. So if f of x is continuous at s is equal to a, or g of x is continuous at s is equal to a, so we just simply use x to replace a, use a to replace x here. We also use a to replace x here. So, but if, for example, let me just review some content we just learned in last semester. That when you just, I ask you to calculate this, like s plus 2, s minus 5. It's easy, right? Because these two functions are continuous at s is equal to 2, right? So if we just encounter this question, that we just normally just replace here by 2 and here by 2. So finally, the result will be 4 over minus 3, right? But if one case that just like s minus 2 and just like this, we also learned this before. We can factorize it, but you can also see if I simply use 2 to replace s here, use 2 to replace here, you can find it will be 0 over 0, right? But it's lucky for x. This part, we still can get its limit because we can factorize it. We can factorize it. Then we can cancel part of it, and then we can get the result. But for most of the indeterminate forms, it's not that easy to get the result. So right now we just learn this L'Hopital's rule. So if suppose that f of a and g of a is equal to 0, are equal to 0, that f of x and g of x are differentiable function on an open interval I containing a and g prime x is not equal to 0 on I if s is not equal to a, then limit s is approaching to a, approaching a, f of x over gx will become limit s is approaching a, f prime x over g prime x. So what do I mean? When I use a to replace x here, we can get 0. And when we just use a to replace x here, we can also get 0. So you can see when we use a as the input for x here or for here, then we can get 0 over 0. So you can see it will be 0 over 0. So this is also 0 over 0, but it's lucky for us to factorize it. But sometimes if it cannot be factorized, you cannot easily to cancel some terms for the both parts. At that time, you should use the L'Hopital's rule. So you can just differentiate f of x first to get f prime x. You can also differentiate g prime x, gx to get g prime x. Then the limit, when you take the limit as x is approaching a, that will be equal to limit s is approaching a, f prime x over g prime x. So if this part is continuously differentiable, if here when use a to replace here, a use here, then it's still 0 over 0, then you can continue to differentiate, and then you can try double differentiation, the second order of differentiation, the derivative for f of x over g double prime x. So you can continue to do that until one of them is no more zero. Then you can start. And then you can get the result. So I will show you an example that, for example, limit x is upon 0, square root of 1 plus x minus 1 minus x over 2 x squared. So in the beginning, if you encounter this, just simply use 0 to replace x here. So you can see, if I use x as 0 to replace x, you can get here is 1, then minus 1, then minus 0. So 1 minus 1 is 0, right? 0 minus 0 is 0, right? For the denominator part, you can see 0 squared. So you will find it will become 0 over 0. See? If you use 0, 0, 0 here, finally you can see the total result will be 0, right? And here is also 0. So we can get it is a 0 over 0 pattern, right? It's an indeterminate form. So the next step is we can just differentiate the numerator and denominator. Again, then you can get, it will be 1/2 times 1 plus x to the power of minus 1/2, then minus 1/2. Then the denominator part is 2x. Denominator part is 2x. So finally, you can still use 0 to replace 0 here. X here. So you can get here 0, 1 plus 1. 1 plus 0 is 1. So this part is still 1/2, minus 1/2. So you can see, I just continue to do that. 0, 0 here. So finally, you still can find this part is 0. This part is still 0. So again, it's still a 0 over 0. Still 0 over 0. So we can continue to do that. That will become limit x is upon 0. Then minus 1 over 4 times 1 plus x times 1 minus 3 over 2, right? And then over 2, right? Continue to differentiate. If you still encounter 0 over 0, then continue to differentiate these two parts. Then here you can see, I can continue to do that. I use 0 to replace x. Then we can get the result is minus 1 over 4, then over 2, right? So here you can see this part is no more 0. Is no more 0. This part is also no more 0. So you can also simply replace x here by 0. Then you can get the result is minus 1 over 8. And then this is the result. So through this example, you can just try to differentiate numerator and denominator again and again. Here it is no more 0 over 0 form. Okay. So let's just stop here for a while and take 10 minutes break. The example that just like this, that limit s is upon 0, 1 minus cosine x over x plus x squared. So you can just find the example. You cannot factorize this term, right? Not like this one, not like this one. This one you can factorize it so that you have common term for the denominator and numerator. So you can just cancel them. But you can see here, if you just use 0 to replace x, use 0 here, 0 here, you can find eventually you can have 0 over 0, right? But you cannot factorize this one. So not to mention you want to cancel them, right? So if so, you can just use L'Hopital's rule to solve this problem. So based on this, you can find it's a 0 over 0 form. So it's a indeterminate form. So we can just differentiate the numerator and denominator. So we can have sine x over 1 plus 2x. And then use 0 to replace x here and here. Then you can see sine 0 is 0. Here is 0 over 1. So here is no more 0 over 0 form. So the final result will be 0 over 1. So the result is 0. So please do not continue to differentiate sine x and 1 plus 2x, because you should stop here. You cannot continue to have the differentiation process for these two terms. Okay, so this is a simple example. So that I just want to give you a note that the so-called indeterminate form could be 0 over 0, infinity over infinity, 0 times infinity times 0, or infinity minus infinity. So these four forms, if you just encounter these four forms, when you calculate the limit value for the form, you can just use the L'Hopital's rule. And the second thing is about the s is approaching a. Here can be s is approaching a plus, or s is approaching a minus. And besides, a also can be finite. That means a certain amount of number, or infinite, like positive infinity or negative infinity. So I also give you an example that if I ask you to calculate s is approaching 1/2 pi secant x over 1 tangent x, right? So you can just, did you remember when we just, this is a two-sided limit, so we can just separate it into two parts. One is limit s is approaching 1/2 pi plus, and consider this one, right? We can separate them into two parts. Right? So, for example, if you focus on this part, we can get, it will be, you can see when you just use 1/2 pi plus to replace x and use this to replace x, you can find it will become positive infinity. And this part will also become positive infinity. So finally, you will find it will be infinity over infinity. So it is also indeterminate form. So that you can just continue to calculate its limit by differentiate second x. So when I differentiate second x, we can get second x tangent x. When we differentiate 1 plus tangent x, we can get second square x. So that you can just cancel it 1. Then we can get this part is sine x over cosine x. This part is 1 over cosine x. So finally, the result will become limit s is approaching 1/2 pi plus then sine x. Let me just repeat the process again. You can see if I just direct use 1/2 pi plus to replace x here, you can get it will be infinity. You will get infinity. If you use 1/2 pi plus to replace x here, you also can get infinity. So you will have infinity over infinity form. It's a indeterminate form, just like 0 over 0. So we can just continue to differentiate it, right? We can differentiate it, then we can get second x times tangent x. For this part, when we differentiate tangent x, we can get second square x. So we can cancel the common term, then we can get second x. Then we just replace tangent x by sine x over cosine x. And this part is 1 over cosine x. So cancel cosine x, cancel cosine x. So we can get sine x. So finally, the result will be 1. So likewise, you can also get the result is also 1. So you can get the right hand limit is 1 and the left hand limit is 1. So we can conclude this result is 1, right? Because so this part is 1. I just want to emphasize that we are considering the left hand limit. 我们在考虑它是什么？左极限。那这个上的右极限，那我们它的右极限算一算是1，对不对？它的左极限你也可以用相同的方法做出来，也是1。左极限跟右极限相等，我们说过它的双边极限存在，所以我们可以说。记得吗？这也是上学期的东西了，在算极限的时候。不，这里的重点是什么？是你用罗必达法则，也可以用在这种所谓的单边极限上面。罗必达法则也可以同时用在，你看这 S 趋近2/2 派，它可以用在 S 趋近正无穷大、负无穷大这种无穷大的极限。好，就是你的极限的 approach 是无穷大的时候，这种极限也可以用罗必达法则。Okay, so I will continue to introduce the indeterminate power like 1 to the power of infinity, or 0 to the power of 0, and infinity to the power of 0. So in the past, actually, it is not, these forms are not legal, right? We don't have so-called 0 to the power of 0. We even don't have infinity to the power of 0. But since it's, if you can encounter such kind of form, again, the result is really hard to say. 如果你遇到的是这种一的无穷大乘以无穷次0分之0，无穷大分之0，这个其实也是一种不确定型，它的值也是不确定，你要去算啊。那其实这边的0分之0其实也不完全0分之0，零的0次方嘛，这不能看成0的0次，为什么？它基本上是一个很接近0，它的次数很接近0。这个是1的意思是，它的比是很接近1，它的次数是很接近1的。所以 ，so let me just give you one example that normally we will follow this mechanism to solve this problem. So if we can get limit s is open a ln f of x is L, then we can get limit s is open a f of x will be limit s approaching a e to the power of ln f of x. Then the result will be e to the power of L. So later on, I will follow this process to get the answer for these forms. So let me give you the process again. Actually, I just want to know limit s is equal to a f of x. I want to know the answer. So maybe I show here. To find, I just want to find limit s is approaching a f of x. This is my purpose. I want to get the answer. I want to get the answer. But if it is related to exponential, then I may suggest you to take ln first. Take ln function value first. Then you need to return to its original text. So if I just take, I can get, when I take limit x is approaching a ln f of x is, I can get this result. Then actually, if I want to get this limit, then the result will be e to the power f. So I just hope you can just keep this in mind, and I will give you an example that, for example, just like if I want to calculate infinity to the power of 0, what is the result? So how can we just solve this problem? So I can construct a function. So I just let f of x is equal to s to the power of 1 over x. So when I want to get the result, I just simply calculate limit s is approaching infinity f of x. It will become limit f approaching infinity s to the power 1 over x. So you will see that we can get infinity to the power of 0, right? So if I can if I want to get this result, I want to get infinity to the power of 0. I want to get infinity to the power of 0. I just construct a function like this one. So if I construct a function like this one, when I calculate its limit for s is approaching infinity, we can get a result, right? So the key tip is I assign this one. Then I gradually to calculate this one. Then I can get the result, right? So then since I just construct the function is just like this one, so I just take ln function. So I take ln function s to power 1 over x. Then I continue to take limit s is approaching infinity, limit s is approaching infinity. So I can get limit s is approaching infinity. I can move here to become the coefficient, so it will become ln x over x. So you can see we can encounter infinity to infinity over infinity. So we can just continue to differentiate limit s is approaching infinity, differentiate 1 over x and 1. So finally the result is 0. The result is 0, right? But don't forget the result is for this limit s is approaching infinity ln f of s is 0. But don't forget our purpose is we want to get limit s approaching infinity f of s without ln, right? Please make a comparison. This is just a temporal process. We take its ln function's value, but eventually this is what we exactly want, right? So if we want to get this one, that it will become limit s is infinity e to the power of ln f of x. So see, we just use the property again, right? E to the power of ln f of x will be f of x. Exponential function, composite ln function, we can get this identical function. So that f of x here as an input, we can also get f of x as its output. Right? Then based on this, here we can get limit. It will become this part will become 0, right? Because here is 0, right? So finally the answer is 1. The final answer is 1.所以我很简单的跟大家解释一下，这个很重要哈，这部分很重要哈。当我们要去算一的无穷大次方，好，说事实上那个一不是真的一，其实你们学过这个，我们学过这个很有趣的现象了哈。如果你要说，我等一下花一点时间再讲回来这里哈。我们如果要说一的无穷大次方，基本上它不是，它是表达成什么？这个是一个很接近一的数，很接近一的数，自己乘了无穷多次。这答案是什么？你们学过了。我先问大家，一乘以一是多少？一乘以一再乘以一， 一乘以一乘以一，好多个一还是一，对不对？当这个很接近一的，自己乘很久以后呢，这答案是一。它这个一跟那个一不一样。其实我们有学过呢，在哪里学过 ？limit s 趋近于无穷大，一加上一除以 x 的 x 次方。仔细想一想，是不是这个结果？这个是一个很接近一的数字，很接近一的数字，自己乘了无穷多次，结果很有趣，出来的结果是一。此一非彼一啦。这个其实我们学过哈，这之前有证明给大家看过。你可以用现在所学到这个法则去证一次，它也是一，它还是一。哦，这个部分课本有，所以我就没有特别讲。但是我们确实学过这个东西。那我现在要讲的是什么呢？是这个。In general， 你如果遇到这种情况的时候，你要去 construct 一个方选。哦，那你要去 construct 方选才是它最重要的第一步骤。那它的一般性的法则是这样子哈，就是说你实际上你是想要得到 limit x 趋近 a 的 f of s 的极限值。可是如果你遇到有这种指数型的，你要先取 ln。为什么取 ln？ 因为 ln 会让你的那个幂次掉下来，比较容易算。但是这是你取巧做了一个步骤，去把那个幂次掉下来。可是你最后要还人家啊，对不对？你取了这个以后，你还要用一把它取回来，所以你去观察这个式子 f of x 有没有等于这个。再看仔细一点，这个你也学过，为什么？一的 ln 的某个什么东西出来的东西就会是这个东西 identical， 对不对？所以如果有这个跟这样的一个关系，最后又因为你知道这个的极限 l， 最后结果是一除以 power。这样讲很模糊，我们就马上举个例子给大家看。好，我要你去算无穷大的零次方是多少，所以我就建构了一个函数，叫做 x 的一除以 x 次方这样的一个函数。仔细看哈，为什么我建构 x 除以 x 的一次方？当我 s 带无穷大的时候，这边是不是无穷大？幂次呢？0，为什么？因为一除以一个无穷大是0，对不对？所以这个就是一个无穷大的零次方的概念。所以我的目标，所以我的目标，如果要算出这个无穷大的零次方的话，等同于什么？我在建构 f of s 是这个函数的情况之下呢，取 limit s 趋近无穷大。大家看一下，如果 limit s 趋近无穷大，是不是就是无穷大的零次方出来了？所以等同于做这个。所以我建构的这函数目标希望取这个极限，但是要取这个极限呢，我用了一个技巧，我要算这个之前，我先取一个让它取 ln 的目标是什么？让它的幂次可以掉下来，对不对？所以当我取了 ln 的 f of s 的时候，这个 s 分之一可以让它从半空中掉下来，就变成什么 ln x 除以 x。这时候去取极限，的时候，它是一个无穷大分之无穷大的不定型。我们是不是可以利用罗必达法则？好，这是无穷大分之，所以我就上下微分。ln s 的微分是什么 ？s 分之一。一的微分是什么？是一。所以当一除以 x 除以一的时候，有人不是0了，对不对？有人不是无穷大的形式了，这时候你就可以把它带进去，得到结果是0。所以这时候的0代表是什么？当你取了 ln f of s 以后的极限，不要忘了你的目标是要算没有 ln 的这种函数的极限哦。 所以我们要回归到我要目标是要算 limit x 趋近无穷大的 f(s)。所以这个时候什么？回归到 f(s) 事实上是等于1的 ln f(s) 的幂次。那这部分你已经算出来了，是0，所以是1的零次方，所以答案是1。所以我们不是说任何数的零次方都是1吗？包含无穷大的零次方也是1。事实上，它这个不是真的零次方，是很接近哈，因为它是极限的概念，它不是真的零，它不是真的无穷大，是一个极限的概念，所以你必须在这里。但是你的形式态上写起来是无穷大分之0，事实上它无穷大是趋近无穷大，幂次趋近于0。So I hope the explanation can make you feel better for this part. So I also list some questions for your reference so that when you just go back, you study the concept and then you can just practice it then by yourself. Okay, so maybe we just stop here because we almost run out of time. We just have 20 seconds. So let's just call it a day. Okay?